The rudder evolved from the steering board that was used in ancient times. The steering board was usually mounted on the right-hand side to suit right-handed sailors. In time, the steering board moved onto the centreline, through a stock passing through the vessel. A tiller was then attached to the stock, allowing sailors to control the rudder from the main deck. The basic setup continued right up until modern times. This is the rudder of the Olympic, and you can see that it carries the same characteristics as the original steering board. It's a small, flat board mounted on a stock passing through the ship. Let's have a look at how this one works. Here we have a simple hull, and I'm just going to attach a normal rudder to the stern. If we keep the rudder amidships, we can watch how the water flows around the hull-rudder combination. It flows evenly, and this means there's no turning force generated, so the hull should move in a straight line. If we now turn the rudder to port, we can see the effect it has on the flow of water. This board-type rudder has now directed the water in a different direction. The water has been directed at an angle away from the boat. The extra water increases the pressure exerted on this side, and decreases the pressure on this side. This pressure difference pushes the stern in this direction, inducing the desired turn to port. As the speed of the water increases, the effectiveness of the rudder also increases. This is why your rudder appears more sensitive at higher speeds. But what if we now change the shape of the rudder slightly? We could make it resemble the wing of an aircraft. Aircraft wings generate lift by forcing air to flow quicker across the curved top surface of the wing. This kind of sucks the aircraft into the air, and is far more efficient than just using a flat wing at an angle. If we apply this principle to a rudder, it gives us this new shape. We'll call this the aerofoil shape. Again, when the rudder is amidships, there's no deflection in water flow, so the boat remains in a straight line. If we turn the rudder, again the water is going to be deflected off to one side. This time, however, the shape of the rudder forces the water to run over a curved path. The water on this side now has to flow faster to flow around the rudder. The water on the other side, conversely, has to flow slightly slower. This speed variation adds to the pressure difference generated by deflection alone that we saw before. This side is actually higher pressure than it was for the flat rudder. Likewise, this side is even lower pressure than it was before. All this means that for a given speed of water, the curved aerofoil-shaped rudder will turn a boat more efficiently than a flat rudder. What if we modify the shape further still? This time, we're going to add an additional flare at the end. We call this a fishtail or a shilling rudder. They're used a lot on ships to improve manoeuvrability at slower speeds. Again, the water flows evenly around the rudder when it's amidships. This time, when we turn the rudder, we can see the additional water deflection. We have the same initial deflection as we did with the board rudder. We have the flow speed differential that we did with the aerofoil. And now we have the additional deflection created by the flare at the very tail of the rudder. This reduces that wasted water flow that was previously flowing around the edge of the trailing edge. This combination acts to further increase the efficiency of the rudder. If it's more effective at the same speed, the logical deduction is that it needs less water flow to generate the same turning effect. These sort of rudders are more effective at slow speeds, making them particularly useful for slow speed ship handling. The final type of rudder we're going to look at is an active rudder. If we go back to the aerofoil shape, and this time we're going to break it near the tip. The tip can then be linked to the main body of the rudder by a mechanical linkage that forces it to turn further than the main rudder. For example, if you turn the rudder to 10 degrees, the mechanical linkage will turn the tip a further 10 degrees. This applies throughout the whole range of movement of the rudder. At 35 degrees, the tip would be 35 degrees further, which is 70 degrees from the direction of movement. We call this type of rudder a flap rudder or a Becker rudder. Becker is the name of the man and the company that developed the rudder, so it's actually just a brand, much like Hoover for vacuum cleaners or Jacuzzi for hot tubs. When we look at the water flow diagram for a flap rudder, we can see again that amidships there's no turning force generated. When we turn the rudder, we have the same change in water flow as before. Much like a shilling rudder, the flap rudder generates that additional increase at the tip. This time, however, the increase at the tip continues to increase even further the further you turn the rudder. When the rudder's hard over, the tip is practically directing water sideways. This makes the flap rudder one of the best options for very slow speed ship handling. The rudder's very effective at slow speeds. With all of the rudders that we've looked at, you've seen that water flow is needed for them to work at all. On a sailing boat, the boat needs to be moving for the rudder to have any effect. On a motorboat, or on ships that are powered by engines, you've got two options. Either you need to be moving through the water, or the propeller needs to be turning, pushing water across the rudder. If you're trying to manoeuvre at slow speeds, you don't want to have the engine running all the time. You're only going to pick up speed. You can use small bursts from the engine to generate the same effect. You move the rudder over, give a kick ahead, you're going to get the same turning effect while minimising the build-up of speed. Another thing to think about with rudders is that you don't want them to stall, in the same way that if an aircraft points up too sharply, they'll stall. If you turn a rudder too far, it's going to stall. Hopefully you found the information today useful. Until next time, thank you for watching.